Today we're going to talk about the titration curve and the equation that goes along with it. And so we want to talk about why we would use the titration, the actual lab, the setup of it, and then how we interpret its results. So before we do any of that, we need to know a few vocabulary words. So the first thing that we need to know is a titrant. And a titrant is going to be the solution with the known concentration. Okay. And in an actual lab setup, it's found in the burette. Okay. The analyte is going to be the solution with the unknown concentration. And it's found in the Erlenmeyer flask. So I'm just going to write flask. Okay. The equivalence point. So we are going to, in a lab, you are going to continuously add titrant to your analyte until you have reached the equivalence point or the end point. So basically what your equivalence point is when the moles of H plus are equal to the moles of OH. It's when you have exactly neutralized your acid and your base. So in a lab setup, the titrant is either going to be the acid or the base, and then your analyte is going to be the other one. So your equivalence point is when the moles of the hydrogen ions that are part of your acid are equal to the moles of your hydroxide ion that are part of your base. And the way that you can see this is through an endpoint. What you're going to try to do is you're going to try to pick an indicator. Remember, our indicators of acids and bases are things that change colors when you go from acidic to basic. You're going to pick an indicator that has an endpoint really close to your equivalence point. So the endpoint is when the indicator changes colors in a titration lab. And if you pick a good indicator, well then your endpoint and equivalence point are about the same, and so you know you've reached the end of your titration. So let me just show you how this works. So the point of a titration is to determine the concentration of your analyte. So here we have a burette, here we have an Erlenmeyer flask. And within your burette, you're going to have titrant. Okay, so you're going to have a solution, whether it's acidic or basic, and it's going to be in the burette. You will know the concentration of this titrant. Okay, and then in your Erlenmeyer flask, you're going to have some unknown solution. You're going to know what it is, but you won't know the concentration of it, right? So it has the analyte. And in here, you're also going to put some sort of indicator so you will know when your equivalence point has been reached. So basically, we continuously add titrant into our analyte until our indicator has changed colors. So then we went from clear to blue, and that's when we have reached the end of our titration, and then we can use an equation to figure out the concentration of our analyte. So if we were to graph the data that you got from that experiment, you would graph something that looks like this. This is called a titration curve. And you graph the milliliters of titrant added, okay, so that's the amount of solution that you add from your burette, and then the pH of the solution in your Erlenmeyer flask. So let's say that within our Erlenmeyer flask, our analyte was an acid. So we would be starting at a really low pH, since acids have low pHs. And it would keep getting a little bit higher, until we've reached a point where we're really close to the equivalence point. And when we're really close to the equivalence point, our pH shoots up quickly. And then once we go past our equivalence point, we are totally basic. So our equivalence point on our titration curve is halfway up the straight line. Okay, so halfway up the straight line. Okay, so sometimes I'll be right at 7, right at neutral, but sometimes it won't be. So it's just halfway up our straightaway. Okay, everything that is below a pH of 7, we consider acidic. Right at 7, so right there, okay, that is neutral. And everything above 7 is a base. Okay, so I can ask you questions about this graph, and a lot of it's just going to be reading the graph. So where is your equivalence point? It's halfway up the straight line. Where is your acid? Where is your base? Where is it neutral? Maybe what is, or how much titrant is needed to get the pH to be about 12. So you'd go over to 12 and go down and figure out your volume. It's just reading the lines on a graph. Now, if we actually wanted to take our titration and figure out information about it, so figure out the concentration of the acid or the analyte, whatever it was, with the lab that we did, we're going to have to use this equation. So this is known as our titration equation. And it's NABA times NA is equal to NB times BB times MB. So the A's all stand for the acid side, and the B's stand for the base side. So Na is the number of hydrogens in the acid formula. The Va is the volume of the acid, and then the Ma is the concentration of the acid. Your volume can be in liters or milliliters, okay? And then your concentration will be in molarity. And then your other side of your equation is the number of hydroxides in your base. Then your volume of your base, again, that can be in liters or milliliters. You just have to make sure that your volumes for your acid and the base are in the same unit. So liters, liters, milliliters, milliliters. And then your concentration of your base will be molarity again. So let's go ahead and apply this equation to some example problems. All right. So I'm going to go ahead and put my equation up here so that I know what I'm plugging into. All right. So it says determine the concentration of sulfuric acid. So I need the concentration of sulfuric acid. So because it's an acid, the concentration of my acid is unknown. If 13 milliliters are titrated, so it's telling us that 13 milliliters of sulfuric acid are being titrated. So that's the volume of my acid, okay, with 14 milliliters of a 2.00 molar NaOH. So we know that NaOH is a base, so this information and this information goes along with the base. So the volume of our base is 14 milliliters. The concentration of my base is 2.00 molar. And so the only things that I still need are the Na and the Nb. Well, I gave you the formula of your base. So now we're just figuring out how many hydroxides there are. There's only one in this formula, so that's a times 1. Now I didn't give you the formula of sulfuric acid, so you first have to write it. Because there's no hydro in front, we know that it's a ternary or an oxyacid. So we know that our cation is hydrogen, and it has a +1 charge. The ic ending comes from the 8, so we know that was sulfate. And the formula for sulfate is SO4 with a -2 charge. So if we crisscross our charges down, we get H2SO4. So if we look at that formula, there are 2 hydrogens, and so this number becomes a 2. So now it's a matter of algebra, right? Solving for x. So we're going to divide both sides by 2 times 13. And x will equal 1.08, and it's molarity, so it's molar. Okay? So when you're thinking about significant figures from here, we're thinking about the sig figs that were in the problem for us. So there were 3 sig figs, 3 sig figs, 3 sig figs. So our answer needs to be the 3 sig figs. We will never use the Na or the Nb because that's just the count of hydrogens and hydroxides. All right, last example. It says, so again, we're using NaVA Ma is equal to NDVB NB. Okay, so we want to determine the volume of a 0.500 molar CaOH2. So this we know is a base because there is a hydroxide on it. So let's fill in our base side first. So it says determine the volume, so that's going to be my X, of a 0.500 molar, so that's the concentration of CaOH2. Okay, and now if we were trying to figure out NB, you look here and there are 2 hydroxides, part of CaOH2, so that's a 2. Okay, needed to titrate 20 milliliters of a 1.50 molar hydrophosphoric acid solution. So all of this information right here goes along with hydrophosphoric. So it tells me that my volume is 20.0 milliliters, tells me that my concentration is 1.50 molar, and now I have to figure out what hydrophosphoric acid is. Because there's a hydro out in front, I know it's a binary acid. So that means I'm starting with hydrogen, and then phosphoric comes from phosphide, okay? So which is which is P, right? But because it's an anion, it has a -3 charge. We crisscross down, so it's H3P. So then our Na is 3 because there are 3 hydrogens, part of H3P. Now I solve for X. So I divide both sides by 2 times 0.5. And I do that to both sides. So X will equal 2 times 20 times 1.5 divided by that, 90.0 milliliters.